this is a long title. Advanced is quicker to write, but yeah, I don't know if it's scarier than completing the square and long division. Those are two of the most feared parts of math.
Are there going to be problems that are straightforward, like just solve this, like
Yes. Yeah. Now, I mean, there will be some. Remember, this section goes all the way back to things like Riemann sums. So there will be some that are more in context that involve some other topics. But when it comes to a lot of your integration stuff, there may be just problems that look like this. Okay. So, all right, so for this problem, I'm trying to even think, can it be done? It can probably be done using U to U substitution, where we solve for the x right here, but it is going to be, it's going to be difficult to do it that way. So, if the numerator, or the degree of the numerator, I should say, the degree of the numerator is 1 greater than the degree of the denominator. Try long division. So, we've got second degree in the numerator, first degree in the denominator. So, Coach Wood taught you long ago how to do long division of polynomials. Okay. So, if we do long division of polynomials, we're asking ourselves, what times 2x plus 1 would give me 12x squared? And so you're really thinking, like, what would I multiply by 2x to get 12x squared? So that would be 6x. Then I will multiply it. So 6x times 2x is 12x squared. 6x times 1 is going to be plus 6x. And then we got to subtract. So these will cancel as they should. We're going to get a negative 6x. We would bring down if we had anything over here to bring down, but we don't for this one. So now we're asking ourselves, what times 2x would give me negative 6x? What would that be? Negative 3. So we got negative 3. So we got negative 3 times 2x is negative 6x. Negative 3 times 1 is negative 3. We are going to subtract, which actually makes both of these positive. Cancels that out. We get 0. We bring down. We've got a 3. Is there anything that we can multiply 2x by that would give us a 3? Well, kind of, if we want to get negative exponents, but we would rather not get negative exponents. So 3 is our remainder here. So the way we're going to write our remainder is we're going to put plus 3 over 2x plus 1. So 12x squared over 2x plus 1 can be written can be written like this: 6x minus 3 plus 3 over 2x plus 1. Do you guys remember doing that long, long, long ago?
Billy did not teach me.
If you had Billy, there's a good chance he did not teach you that. Coach Wood did it. Those of you that had Coach Wood.
I mean, he would have called him that.
Coach Wood decided to not be there the day that he gave this, so I had to go up to the board.
Gotcha. Gotcha. That's a doozy to leave on the day you got stuff. But it was at least attempted to cover it at some point there. So it is like long division, but you're asking, instead of saying like what times 10 would give me, like to subtract like you would do regular long division, it's what times this first thing would give me the 12x squared. You multiply that, subtract, bring down. Then you'll do the next what times this would give me what I'm trying to get now. Subtract, bring down, until you get something that has a degree that's less than your divisor. So like here I don't have any more x's, so there's nothing I could multiply by here easily. And then your remainder is just going to be whatever you had as your remainder divided by the 2x plus 1. So we might need a little extra on that. This is not the sort of stuff you're going to see a lot of problems on, but you may see some problems on it. So what's good about this is I can treat this as separate integrals now. This is 6x minus 3 plus the integral of 3 over 2x plus 1. And I would wait until the end to integrate. So like we could integrate 6x minus 3 really easily because it's just the power rule. But I would wait and integrate both at the same time, because then you can just put one single plus c on the end. And you don't have to have separate plus c's that you combine. So if I'm looking at just this part right here, the u would be 2x plus 1. The du would be 2 dx. I like to just take this 3, pull it out front, so that I don't have to deal with it, since it's not the number that needs to go in my dx. Then I have to put a 2 right here, which means I will multiply by 1/2 out front. You can, yes. Yeah. And so this part right here is my u. This part right here is my du. So, again, I'm leaving this alone because technically you should integrate these at the same time if you're just going to use a single plus c on the end. So we got 3/2 integral of 1 over u du. Okay. What do we get when we integrate 1 over u? Natural log. So we're going to integrate 6x minus 3. So that'll be x squared. Divide by the 2. You'll get a 3 for your coefficient here. Minus 3x. Plus 3/2 natural log of the absolute value. I could go ahead and I could put the u there, but if you want, you could just go ahead and plug your u back in. 2x plus 1. To save you a step there. And put a plus c on the end. And it looks like that, no, let's see. C, is that right for C? Yeah, C would be your answer there. So once you do the long division, you should be left with a fairly simple u du that's going to give you a natural log.
On
pretty much because that numerator is going to be like 1 greater than the denominator. So when we get to this part, it's not a lot different than stuff we've done before. It's the long division that is more difficult, and considering that it seems we have a very limited background on long division, we may need a little more practice with that. All right. Okay. Now, my least favorite of all integrals, inverse trig integrals. Do you guys still have your note card for inverse trig derivatives? Okay. You may add these to that note card, and this note card may be used on quizzes or tests. If you do not have it anymore, I can give you a new note card.
No way.
Anybody need a note card? You actually have it.
It's a shake leg back. Yeah, I remember that.
Anybody else need a note card? It's been a while. Everybody got a note card? Okay. So I'm not going to make you memorize these. We do have to memorize them before the exam, but we will just cram and memorize them before the exam. Because you will forget them, I'm sure. Because I don't know them well. And this is like my 6th or 7th time teaching. 7. You will have to have it memorized for the AP exam, because they do not give this to you on the AP exam. For my test, until we get to the very end when we're doing reviewing, so like on this test, I will not require you to have them memorized. You may use the note card. If it happens to show up in anything else we do until the very end, you can use the note card. You do have to have it memorized for the exam, so it's going to be one of those things that, like, the week before the exam, we're going to try to, like, cram and make sure we have it memorized then, because I know this is one of those things, like, you're going to memorize and forget quickly. So...
Alexander the Great, Ulysses Grant. No, plus Connor.
That's appropriate. C is the unknown variable, and you never know exactly what Connor's going to do. So.
Every problem ends with plus Colombian Band. Never forget Colombian Band.
Since I think that's probably a drug reference, we're not going to endorse that. Although sometimes those things are the best way to remember things because they stand out in your memory.
You'll never forget.
Private showing of cocaine.
I would. I don't know.
Colombian.
Maybe.
All right. Okay.
Because did she tell you?
So, all right. Let's. All right. All right. Let's look at an example. Copy this example down. Yes. Senior plays one of my favorite things.
Grace and I will be here at the opening number. No, I don't have to see it. I don't have to see it. With everyone. I'm gonna do it.
All right. Inverse trig is one of my least favorite things because it is mostly knowing those formulas and like having it pop out at you that it is going to be used here. But it helps if it is multiple choice because these answer choices here make you think, oh, I should check that note card, right? That it might apply. So our rule for sign is, what is it, 1 over, is it u minus a, or a minus u, a squared minus u squared, a squared minus u squared. Du equals arc sine, or sine inverse of u over a. This one does not have the 1 over a out front, does it? The others do, okay. So, you can see here that we've got 12, which could be an a squared. It's not a perfect square, which makes it aggravating, but yeah. Roots. Okay, I know where it's going to come in. Okay. All right, so we got a 12. We got minus this stuff over here, but we do not have like an a squared minus a u squared underneath our square root. So what we can do is we can complete the square to get it in the form where we have a squared minus u squared. So this is how that will look. I would just take this 8 from the numerator and go ahead and pull it out front so that it's not an issue. And then I'm going to leave this 12 right here. I'm going to take the negative right here and factor it out of those last terms. So we're going to have x squared plus 4 squared, or 4x plus blank. Okay, so what we're wanting here is to have 12 minus, we want to have x plus something squared. We want this to be a term that is squared. So we are going to complete the square to make that happen. So if I divide this 4 by 2, I get 2. That's the number that goes here. And then square, double square, what number needs to be added in my blank right here? 4. But I can't just add a 4 there without balancing it out. So, although I added a 4 here, it's really like I subtracted it because of this negative, right? Remember, we have to, when we do complete the square, we have to take this number, multiply it by this right here. So it's like I subtracted 4, but I can't subtract 4 unless I also add 4. So this 4 right here, although it looks like a plus 4, by the time I distribute that negative, it would be like I subtracted 4. So if I subtract 4, I've got to also add 4 to cancel out what I've done there. So I'm not actually changing the value. Does that make sense? All right, so this 12 and the 4 I can put together. So that's going to look like this. 1 over 16 minus x plus 2 squared. Anyway, I should have been putting a dx over here on the end the whole time. All right, so if I'm using this rule for inverse sine, then this, what should my A value be? It's 4, because it's squared, right? So if I wanted to, I could write it this way. Instead of writing 16 right there, I could write 4 squared. So my A is 4, my U is x plus 2. What's my du? It's just 1 dx, so you don't really have to do anything special there. If you had a number right there, if you had like a 3, then just like we've done with the others, you need to put the 3 there with your dx and a 1/3 out front. So our rule tells us that we will get, our 8 is going to stay out front. We'll have sine inverse of u, which is x plus 2, over d over a, which is 4, and we'll have a plus c on the end. And to that is answer choice D. The most difficult thing about these is recognizing that this is what you need to do.
Do you use the sign because it's the answer choices?
Yeah, that's the biggest thing, but also this has a square root in it. So whenever you're looking at your possibilities, for arcsine, you have a square root, and you don't have anything on the outside of the square root. Arcsecant, you have a square root, and you've got this like u out here on the outside, so you have like another variable out there. Tangent, which is the one that shows up on the actual exam the most, it does not have a square root. I don't know that on the actual exam, which they have not shown us the multiple choice in several years. 2019 is the last time they released the multiple choice, or 18 maybe, can't remember. I don't recall ever seeing arcsecant on the actual exam. It is usually tangent. So, it is in the curriculum. It's not going to be tested super heavily by me or by AP for that. Okay, so here is another one. So, this, in the beginning, looks like, especially if you don't have answer choices, because sometimes these might show up on free response, and that's when they really get everybody. Nobody gets those right. That's one of those ones that, like, really helps tell between really a lot of fives are not even getting these right. But this looks like something you could do UDU substitution on, but u would have to be x squared plus 4x plus 8, and du would have to be 2x plus 4, and we can't just make an x appear that's not there. If we have an extra x, we can turn it into a u, but if we are missing an x, we can't just put it in there. So, so UDU substitution is going to fail if you try to just do the normal UDU substitution. Plus, this one's multiple choice, so you can see all those inverse tangents should guide you to believe that maybe there is going to be an inverse tangent problem. So, the rule for inverse tangent is 1 over is it u squared plus a squared, or a squared plus u squared. It really doesn't matter which order that is in. And that is going to give you, that one's 1 over a inverse tangent of u over a plus c. So, so we can complete the square on this one as well. I would take that 4 and just go ahead and get it out of the way. So you got 1 over, And we're going to complete the square, so we've got x squared plus 4x plus blank. And we got plus 8 over here. So if I complete the square, what I'm trying to do is trying to get x something squared over here plus, something else. So I've got the same numbers again. So 4, if I divide it in half, I get 2. Square, double square. The number I need to add right here is 4, just like the last one because we had the same middle term. And so if I add 4 here, what do I have to do on the end? I've got to subtract 4. And this time we are going to subtract 4 because we don't have anything like factored out right there. Last time we had a negative out here, so our adding 4 was really subtracting 4. So I had to add 4 on the end. This time, this is a true just adding 4, so we subtract 4 over here. So that gives us 4 right here, which I can think of as 2 squared. So my u is x plus 2. My a is just 2. You do want to check du, but most of the time for these, they're going to give you ones where you take the derivative, you just get 1 for that. So since this is in that form for inverse tangent, we are going to have 4. We're going to do 1 over a, so 1/2 inverse tangent of u, which is x plus 2, over a, which is 2, plus c. And so half of 4 is going to give us 2 inverse tangent of x plus 2 over 2 plus c. So that is d plus there. It's part of the rule for inverse tangent. You got to do that 1 over a. So since our a is 2, that's where that came from. With sine, it doesn't have that part in its definition, so we didn't do it on the last problem. And you will be allowed to use your note card so that you don't have to have those memorized. Okay, here. Huh? Yeah. What I usually find is like when we get to exam review time, the problem is nobody remembers to do this. Like if I give you, like when I give you homework on this with your note card and all of the problems are like this, most of the time students can do it. It's not the worst thing we've done, that's for sure. But the problem is like being able to pick out when to do it, because the problems don't look like they have anything to do with trig. So to complete the square, like let me just give you a side example for that. So if I have something like x squared plus 12x minus 7, and I want to complete the square on that, so you're going to group your x terms together like that. And if you have anything you can factor out, you want to factor it out. But most of the time, the only thing you're going to take is a negative if you factor anything. So it's going to look like this: x squared plus 12x plus blank minus 7, and then we're probably going to have to add something else over here. So, or subtract, actually. We'll leave that open right there. So, so when you're completing the square, you're wanting to get it to where it's like a square, double square sort of thing, so you can write it as something squared. So the number that's going to go right here is always half of that middle number, because that's your double and you're undoubling it, dividing it by 2. So that's going to be plus 6 for this one. And then the number that would be on the end, you need this to equal x plus 6 squared. So if you square, double square, x squared plus 12x, that's your double. Your square on the end is 36, so you added 36 there. Because this, x squared plus 12x plus 36, factors to be x plus 6 times x plus 6. So it can be written this way. But because I just like decided to throw a 36 in there, I can't do that unless I balance it out with something else. So since that's a positive 36, I'd have to put a minus 36 on the end. So I'd have like negative 42 over here on the end for that. So that's your process for these. The first two were both, like they did, it's not always a 4 and a 2, like it just happened to be for those. All right, here's another one. This one is not inverse trig. This one goes back to our long division problem, so we get a little more practice with that. This one, again, recognizing what to do is the most difficult part of this, but when you see the exponent's degree is 1 higher than the denominator, that is a key that is going to tell you that long division might be helpful. If you try U to U on this, it's not going to work, because if you use the denominator, your dx is just 1, and you have all that stuff on the top. If you have 3x squared plus 2x plus 1 as your u, then your derivative is 6x plus 2, and you don't have that anywhere. So we're going to do long division on this one. And the x plus 2 will go on the outside. 3x squared plus 2x plus 1 goes on the inside. So for long division, I'm asking myself, what times x would give me 3x squared? So 3x, right? So I multiply 3x times x, which is going to give me 3x squared. And then I also have to multiply by that 2. So 3x times the positive 2 gives me 8 plus 6x. So just like division, we divide, multiply, subtract, bring down. So we subtract here, and the 3x squareds will cancel, which is what we wanted. We get a negative 4x here. This time we do have stuff to bring down. We're going to bring down that plus 1. And so, again, we're asking ourselves, what times x would give us negative 4x? It's not going to match perfectly because on these it's not going to divide evenly. So you're really only thinking about what you need to multiply that first term by. So what times x would give us negative 4x? A negative 4. And so we'll multiply now. Negative 4 times x gives us negative 4x. Negative 4 times positive 2 gives me a negative 8. And so we will subtract, which is going to actually make that positive and that positive. And so our negative 4x's will cancel like we wanted them to. I get 9 right here. There is nothing left to bring down. I also don't have any x's with my answer. So this is my remainder right here. And I write my remainder like this. Put the remainder on top. Put what you are dividing by on the bottom. And so it is easiest to deal with this separately. We're thinking of the integral from negative 1 to 1 of 3x minus 4 dx plus the integral from negative 1 to 1 of 9 over x plus 2 dx. And you can do those two parts completely separately and then add them together at the end. So I'm going to work with this first part first here. To integrate that, I would get an x squared. I'll have 3 halves minus 4x. And I'm evaluating that from 1 to negative 1. Negative 1 to 1, I mean. So I'm going to just go ahead and do this whole part. 3 halves times 1 squared minus 4 times 1. minus 3/2 times negative 1 squared minus 4 times negative 1. And so that's going to give me 3/2 minus 4. I'm gonna go ahead and do this minus 3/2. That's gonna be a positive 4, but then I'm gonna distribute this negative right here, and so I'll get a negative 4 right there. So my 3/2 actually end up canceling out, and I get negative 8 for that part. I'm thinking C's looking like a good candidate, but there might be a number that shows up over here. May not. I think it's going to be C though. All right, so that's the first part. Over here, I would need to do a u to u substitution. So u would equal x plus 2. Du would equal just dx. So this part right here would be my u. This part right here is my du. And that 9 right there, I would just pull it out front. So I could change this to the integral, or 9 times the integral of 1 over u du. And I'm just going to switch my limits so I don't have to go back to x's. So negative 1 plus 2 gives me a positive 1, and 1 plus 2 is going to give me a 3. It actually might be D. Let's see. So I've got 9, my integral of 1 over u, what is it? Natural log of the absolute value of u. And I'm going to evaluate that from 1 to 3. No, it's going to be C. So I've got 9 natural log of 3 minus natural log of 1. What is the natural log of 1? It's 0. So since natural log of 1 is 0, I'm just going to get plus 9 natural log of 3, which is C. Okay. Questions?